Now let's continue this bounded sequence. Understand, when you are given a sequence of real numbers, as you can see here, you can call that sequence as bounded above. Look at it. You call this sequence as bounded above if there exists one number m such that all the numbers in the sequence are less than or equal to this particular number. Right? Understand? When you are given a sequence of numbers, if all the numbers in the sequence are less than or equal to one particular number m, remember this m, it may be a number in the sequence or not, not necessarily. It may be one member of the given sequence. That's how you see it may be either equal or less than. If it is also a member of the sequence, we'll get this equality. Otherwise, it is strictly less than m. Right? Anyway, when you are given a sequence of real numbers, if you can find one number m such that all the numbers in the sequence are less than this number, we call such a sequence as what you call bounded above sequence. See here, for example, if I take 1 by n, right? If I take this sequence 1 by n, see, if you write all the numbers from this sequence, see, for different values of n, for n is equal to 1, you will get 1. Then for n is equal to 2, it is 1 by 2. Then for 1 is equal to 3, it is 1 by 3, 1 by 4. All these things you'll get. So when you take all these numbers here, you can easily identify one maximum value in this. See what it is? 1. 1 is the maximum value. You see, the numbers are clearly decreasing order, in decreasing order. Clearly, since you can find one number which is maximum among all these values, you can say all the numbers in this sequence for different values of n are clearly less than or equals to 1. Because 1 is also a member of this sequence, I'm taking equality. Right? Since one highest value can be found from this sequence of numbers, from this set of numbers, I'll say this sequence is bounded above. Right? It is a decreasing sequence clearly, and there is one value which is more than all other values. That's how I'm saying this is bounded above. And whatever the higher value you are getting here, we call this as what you call upper bound. Right? We call this number as upper bound. Whatever the highest value you will get, you will call this as upper bound. Then see, similarly, when you are given a sequence of real numbers Sn, you can call this as bounded below. You can take this as bounded below if you get some other number m such that this number is less than all other numbers in the sequence. Right? Again, the same story, you see, this small m may be a member of the sequence or not. I'm not worried about that. But all the members in the sequence, all the numbers in the sequence must be more than this number. Then we can take such a sequence as what you call bounded below sequence. As you can see here, one example, sequence is simply n. When you write all the numbers of the sequence, you see they are 1, 2, 3, and so on. See, all the numbers in this sequence are more than 1 here. Again, 1 is one of the numbers in the sequence, and this one is less than all other numbers. That's how you can find a lower value here, the lowest value in this sequence. Right? So we call such a sequence as bounded below. And hence, you can also take this, you see, you can take 2 to the power of n. If you take the sequence 2 to the power of n, we'll get these numbers: 2 power 1, 2 power 2, 4, then 2 power 3, 8, 2 power 4, 16, all these things. Among all these things, you see, now this is an increasing sequence. That's how all other members are just above this 2. That's how you can identify least value from this sequence. And when such a least value exists, we'll say that sequence is bounded below. Right? That sequence is bounded below. When highest value exists in a sequence, we can call this as what you call bounded above sequence. Right? That's one idea. And also look at this example. The same thing, 1 by n. If you look at all the numbers of the sequence 1 by n, this one, one point you see, as n approaches to infinity, all the numbers in this sequence 1 by n, they'll go towards 0. But for sure, for no n, 1 by n is strictly 0. Right? You may take n is equal to 1 crore or 10 crores or 100 crores, 1 million, anything is okay. But certainly that is some other value which is not 0. You may get 0 point some 10 zeros, 20 zeros, anything is okay. But I'm not considering that as 0. Right? Only for n is equals to infinity it will be 0, but n is equal to infinity cannot be defined. That's where the problem is. That's how you see, I can say it like this. When you write all the numbers in the sequence, one point, which you have already observed, one is the maximum value. Number one is the maximum value. So this is, what you call bounded above, right? In a similar way, I can say all these numbers in the sequence are clearly more than or equal to 0. I cannot even say equal to 0. They are strictly more than 0, right? Strictly they are more than 0. That's how, though 0 is not a member of this sequence, though 0 is not a member of this sequence, I can take this 0 as a lower bound for this sequence. Why I am taking this as lower bound? Understand? Because all the members of this sequence are clearly greater than 0. This condition is now satisfied, right? I can find one number m and that is 0 here. I can find a number 0 such that all the numbers in this sequence are greater than 0. That's how for this sequence, 0 is what you call lower bound. And of course, 1 is already an upper bound. Remember, 1 is the maximum value, 1 is a member of that, right? So that's how 1 is an upper bound. So understand, this sequence is both bounded above as well as bounded below. So to be bounded above, you must have a highest value. To be bounded below, you must have a lowest value. And you see now, to be bounded, simply, to be bounded, what you call, if you can find both lower bound as well as upper bound to the given sequence, if there exist numbers, both small m and capital M, in the sense, for a given sequence, if you have both lower bound as well as upper bound, then you call normally the given sequence as a bounded sequence. But see, in lighter vein, normally, instead of calling it as bounded above or bounded below, sometimes, we just call it as bounded, right? When we say in our higher classes, normally when we say bounded, it refers to either bounded below or bounded above. Anything may come in general. But strictly speaking, it is bounded when it has both lower bound as well as the upper bound, examples of this kind, right? So that's all about bounded sequence, right? When there is when there is a lowest value in the given sequence of numbers, then you can call that sequence as a bounded below sequence. When there is what you call highest value in the in the numbers of the given sequence, then you can call that as a bounded above sequence. And if it has both lower bound as well as upper bound, normally we take it as a bounded sequence, right? So that's simply about the bounded sequence. Then let me just define you these things. A monotonic sequence, quite simple to understand. Now see, a monotonic sequence, again the same thing, two ways. When you are given a sequence of real numbers, as you can see here, you can call that sequence of real numbers as monotonically increasing sequence, right? This is monotonically increasing sequence. And see here, if you consider any two successive numbers like Sn and Sn plus 1, if two successive numbers in the sequence follow this relation, right? If one number in the sequence is less than or equal to its next number, then we can say that sequence is what you call monotonically increasing sequence. And in a similar way, see, for example, if you take this, like 2 to the power of n. If you take this sequence, you see, if you write all the numbers in this sequence, they are just 2, 4, 8, 16, next 32 and so on. If you take any two numbers in this sequence, the first one is less than the second one, right? Obviously, you can understand this sequence, the numbers in this sequence are clearly in increasing order. When the numbers in the sequence are clearly in increasing order, you can say that sequence as a monotonically increasing sequence, right? And in a way, like, if you take, as you have seen already, 1 by n, if you take this sequence, you see what you have, 1, 1 by 2, 1 by 3, 1 by 4. As you can see, these numbers, they are clearly what you call decreasing sequences. I mean, these are decreasing in order, right? That's how this is a decreasing sequence. When the numbers in the sequence are in this kind of order, I mean, if you take any two numbers in the sequence, if the first number is more than the second number, then we can say this particular sequence as a monotonically decreasing sequence. right? You can take any two numbers in this, any two consecutive numbers in the sequence. You can take any two successive numbers in the sequence, right? Among those two, if the first number is more than the second number, then we say that is a monotonically decreasing sequence. And otherwise, you see, if you take any two numbers, if you take any two successive numbers from the given sequence, if first number is less than the second number, then we say that is an increasing sequence. Okay, so that's simple basic definitions to define about monotonically increasing or monotonically decreasing sequence. And now in particular, you see, in general, for our convenience, we just pronounce it as a monotonic sequence. Monotonic sequence, normally, as you know, a sequence cannot be both monotonically decreasing or increasing simultaneously. But to understand, when we say a monotonic sequence, it is either monotonically increasing or monotonically decreasing, right? Either of the things may follow there. Okay, that's one option. And see here, there are few options. You see, sometimes, two successive numbers in a given sequence may be same also, right? Anyway, here in these two examples, nowhere you will get the same numbers as successive. I mean, no two successive numbers as same. But there are few options, where you may get two successive numbers as also same. In such a case, see, if Sn is strictly greater than Sn plus 1, in a case, if two successive numbers in a given sequence of numbers are same, then there is a possibility of Sn may be equal to Sn plus 1 if two numbers in the sequence are equal. But see, if I exclude this particular condition, if I take strictly Sn as greater than or equal to Sn plus 1, right? I mean, if you take two successive numbers in the sequence, if the first one is strictly more than the second one, then I can call such a sequence as monotonically decreasing sequence. I'm just excluding equality here. And here also the same thing, right? If I exclude that equality, if I take strictly Sn less than Sn plus 1, then I'll call such a sequence as strictly monotonically. In this case, it is strictly monotonically increasing. And here in this case, it is strictly monotonically decreasing sequence, right? But you see, in many of the cases, they are strictly monotonical increasing sequences only, right? In general, as you know, when you write set of numbers, we only write anyway distinct set of numbers. We just exclude, other things, right? But anyway, if there is a chance, they may be equal also, right? If you exclude that equality, we are calling them as strictly monotonically increasing or strictly monotonically decreasing, right? Anyway, if a sequence which is either strictly increasing or strictly decreasing, we simply call it as strictly monotonic. As I told you now, when I say simply monotonic, it may be either monotonically decreasing or monotonically increasing. In a similar way, when I say it is strictly monotonic, right? If I say the given sequence is strictly monotonic, you can understand either it is strictly monotonically increasing or strictly monotonically decreasing, right? I mean, when I say strictly, you can understand no two successive numbers in the sequence are equal, right? No two successive numbers in the sequence are equal, right? That's the only idea you need to remember, right? So two things we have discussed now: monotonic sequence as well as bounded sequence. Let's see a few observations now. Right, look at them. Now see, we have three things which are to be discussed together. When you are given a sequence, it may be convergent, as we discussed earlier. It may be bounded. It may be monotonic also. I'm just trying to combine these three in different statements like this. Look at the first statement here. Every convergent sequence is bounded. As I told you already, when I say bounded, in a lighter vein, we are speaking it as bounded, understand? When I say bounded, it may be either bounded below or bounded above, right? So keeping that idea in mind, what do you mean by convergent sequence? See, when you are given a sequence Sn, let us say, when can you say this is convergent? If limit n tends to infinity exists. I mean, if you calculate this limit, if you get the limit as a finite number, we say it is convergent, right? Understand what it is. When the given sequence is convergent, so if you are writing all the numbers in the sequence one after the other, so when n approaches to infinity, all the numbers in the sequence are going to be in the neighborhood of L. That's why only you are getting the limit as L here. So that When n approaches to infinity, the last numbers here, they are moving closer to L here, right? That's how you can understand if this is an increasing sequence, this L is going to be the maximum value. If this is a decreasing sequence, this L is going to be a lowest value. Anyway, all the numbers are going towards L only here. So if it is an increasing sequence, it is going to be the upper bound. If this is a decreasing sequence, this is going to be the least value or what you call lower bound, right? In either ways, whether it is increasing or a decreasing sequence, definitely you are going to get a boundary here because all the numbers are coming closer to L only. That's how you can understand when it is a convergent sequence, certainly either it is bounded below or bounded above. And that's how you are saying it is bounded here. When it is a convergent sequence, certainly there will be a boundary. The boundary itself is what you call limit, right? That limit itself is the boundary to you. It may be an upper bound or what you call a lower bound. In either ways, definitely when it is a convergent sequence, you are going to get it as a bounded sequence, right? When I say bounded, understand it may be either bounded above or bounded below, right? That's the first point here. And look at the second point here. An increasing sequence which is bounded above is convergent. Now there are 2 points to understand. You are given one sequence which is increasing, monotonically increasing. You can automatically understand that. And also you are given it has a bounded above, right? You are given one increasing sequence as n tends to infinity. The values are clearly increasing, and it is even bounded above, means there is certain boundary at the end. So even n tends to infinity, the sequence of numbers can't go beyond this. All the numbers in this sequence are clearly less than this particular boundary. If you take this as some capital M, all the numbers in the sequence are clearly less than M or less than or equal to M. That is all right. That's how you see you are given it as bounded above. Now see, when all the numbers in the sequence are clearly less than or equal to M, certainly, these things go towards what you call this M only, right? That's how you see when it is both increasing as well as bounded above. You can say when all the values in the sequence are going towards M, you can clearly say the limit is M here. That's how we can say because it is clearly increasing, that's how you say, you can say this is again a convergent sequence. See, for example, if you take this sequence, let us say n by n plus 1. Right, see in this sequence, if you just write all the numbers one after the other, for n is equals to 1, we'll get 1 by 2. Then for n is equal to 2, we'll get 2 by 3. Then for n is equal to 3, we'll get it as 3 by 4, then 4 by 5, and so on. Right? Look at all these values. Are these values increasing or decreasing? That we need to understand first. Right? 1 by 2. 1 by 2 is nearly 0.5. Then 2 by 3 is nearly 0.66. 4 by 3 by 4 means it is 0.7 something. 4 by 5 means 0.8. Clearly these are all in increasing order. So this is clearly an increasing sequence. And now let us see whether it is bounded or not. To understand that, I'm just checking for larger values. If I take, something like 1000 divided by 1001, you'll get this as something like 0.99900 something. Even if you take 10,000 or 1 lakh by 1 lakh 1, you will get it as strictly very much closer to 1. That's how you can understand. If you just continue like this, even if you see, just for verification, if you take limit n tends to infinity to this sequence, clearly, you can take n common from this. So we'll get it as limit n tends to infinity 1 divided by 1 plus 1 by n. Right? See, from the denominator, I took what you call n common, so that I got it as 1 plus 1 by n, and that n, it can be cancelled both in the numerator and denominator. That's how you can see as n tends to infinity here, the limit is exactly 1, which means the maximum value for this sequence of numbers is exactly 1. I mean, all the numbers in this sequence are clearly less than 1. Nowhere you will get 1, remember. For no n, you will get it as 1, but certainly they are all less than 1. That's how you see this is an increasing sequence, and even it is bounded also, bounded above also. And hence you see this is obviously convergent. Right? When you are given a sequence which is increasing and even when it is bounded above, clearly it is convergent. Right? It's quite simple to understand. You see, when there is a particular limit Obviously all the numbers in the sequence go towards that particular boundary only, and therefore thereby automatically it is convergent. In a similar way, when you are given a decreasing sequence, when you are given a decreasing sequence which is bounded below, is also what you call convergent, right? A similar idea you see when you take number 1 by n, I mean the sequence 1 by n, clearly you see it is a decreasing sequence, 1 1 by 2 1 by 3, clearly this is a decreasing sequence, and it is even bounded what you call below, because all the numbers in the sequence are greater than 0. There is a clear boundary for this, right? That's how you see when you are given a sequence which is down, which is decreasing and even bounded below, is again you see if you take limit n tends to infinity to this, we'll get the limit itself as 0. That's how even in this case also you say the sequence is convergent. Now see here the fourth point, an unbounded sequence. What do you mean by unbounded sequence? When there is no boundary on either sides. So when n tends to infinity, see in these examples, if you take it as 2 to the power of n or 1 by n, anything else, like even if you take n by n plus 1, they are having either lower bound or upper bound. But for a sequence, if there is no lower bound and no upper bound, nothing is there. In such a case, we call it as an unbounded sequence. I'll just give you an example here. You see, take it like this. The sequence Sn is equals to, let us say, minus 1 to the power of n into n, if I take this sequence. So when you take n is equals to 1, we'll get it as minus 1. Then for n is equal to 2, it is plus 2. Then for n is equal to 3, it is minus 3. Then for n is equal to 4, it is plus 4. It goes like this. So if you just write them in a proper order, see, we'll get minus 1, 2. Then we'll get minus 3. And here it is 4. Next to this, you see, we'll get all these numbers, 2, 4, 6, all the even numbers comes in this side. And then all odd numbers with a negative sign, we'll get them like this. That's how you see as n tends to infinity, some set of numbers are going towards minus infinity and some set of numbers are going towards plus infinity. That's how you see this particular, sequence has no lower bound and no upper bound. That's how we say this sequence has unbounded sequence. So when it is unbounded, it is obviously not convergent. Why it is not convergent? As n tends to infinity, the sequence, the numbers in the sequence are not going towards a unique value. We'll expect a unique finite value, That's how, as it is going on either sides towards plus infinity and minus infinity both, we can say this is not a convergent sequence. It's a clearly divergent sequence. However, now see, if you are given a bounded sequence, ఇక్కడ మనం ఏమంటున్నాం చూడండి, ఇది అన్బౌండెడ్ ఉంది కాబట్టి బోత్ సైడ్స్ బౌండెడ్ అవ్వట్లేదు కాబట్టి అది కన్వర్జెంట్ కాదంటున్నాం. మరి ఒకవేళ బౌండెడ్ అయితే కన్వర్జెంట్ అవుతుందా? నో, అట్లేం లేదు. Even when you are given a bounded sequence, it need not be convergent, right? See, I'm saying when it is unbounded clearly on either sides, it is definitely not convergent. But what if it is bounded, right? See what happens here. I'll just take one example. If you take this example, minus 1 to the power of n, this sequence. Now in this sequence, when you take n tends to infinity, in fact, for all odd numbers, when n is odd, we'll get it as minus 1. And for all even numbers, we'll get it as plus 1. Right? Whatever may be the value of n, if it is odd, we'll get it as minus 1. And when it is even, we'll get it as plus 1. So clearly, see, this is the sequence of numbers. That's it. You may take any huge n value, we'll get either of these two only. Then that's how you can understand clearly for this sequence, minus 1 is what you call the lower bound and plus 1 is what you call the upper bound. So since both lower bound and upper bound are existing, clearly this is a bounded sequence, right? This is a bounded sequence. Though this is a bounded sequence, since the limit doesn't exist to this, we had seen this yesterday itself. Since as n tends to infinity, since the function, I mean the sequence of numbers are going to two different numbers, we usually expect a unique value, but here we are getting two different values. That's how the limit doesn't exist. When the limit doesn't exist, we cannot say it is convergent, right? So though here it is bounded, we cannot say it is convergent, right? So when it is unbounded sequence, certainly it is not convergent, no other question. But even in few cases, when it is bounded, it may not be convergent, right? And here if you see this one, when you take n by n plus 1, it is also actually bounded. You can see we had seen the maximum value here as plus 1. And what about the minimum value here? Clearly it is 0.5. You see 0.5 is the least value here. All other numbers are more than 0.5 and of course less than 1. That's how even this sequence, all the numbers in the sequence, they lie in between 0.5 and 1. Right? That's how even this sequence is also bounded. And see here, when it is bounded, this is convergent. It is converging to, what you call plus 1 here. Right? So that's how, we are saying when it is bounded, it may be convergent or not. We cannot say anything about it. That's why you see the statement here says, when it is a bounded sequence, we cannot say exactly whether it is convergent or not. It need not be convergent always. Okay. And see, I'm just combining all the other statements here. When you are given a monotonic sequence, maybe maybe monotonically increasing or monotonically decreasing. When you are given a monotonic sequence which is convergent, right? When you are given a monotonic sequence which is convergent, see, we had seen this already. You are given a monotonic bounded sequence here. When it is monotonic bounded, it is already convergent. See, monotonic increasing, bounded above, monotonic decreasing and bounded below, right? So in simple, if you just merge these two ideas, it is a monotonic bounded sequence. When it is monotonic bounded sequence, it is convergent, right? Now just you're writing its converse here. When it is monotonic and convergent also, understand when it is monotonic and convergent, what happens? If it is a monotonically decreasing sequence, we may get a lower limit for this, right? When it is a monotonically decreasing sequence, as n tends to infinity, and you are given it as a convergent also, right? When it is monotonic as well as convergent, and I'm particularly taking when it is a monotonically decreasing sequence, after some values, like when n tends to infinity, you will get a lower bound here, right? When it is a decreasing sequence and when it is convergent, as n tends to infinity, there exists a certain boundary to this, that is what you call lower bound. Or in the other way, when you are given a monotonically increasing sequence and when it is convergent, certainly, you will get a boundary here also. Because it is a convergent sequence, certainly as n tends to infinity, some limit must exist. And therefore, you see, you will get a maximum value, which is what you call upper bound. In either ways, when you are given a monotonic sequence which is convergent, strictly, it will be bounded also. When it is monotonically increasing, you will get it as bounded above. When it is monotonically decreasing, you will get it as bounded below. And either ways, in general, when it is monotonic sequence which is convergent, it is obviously bounded also. And that's how you see, we are taking it as if and only if, they are converse to each other. When it is monotonically sequence and convergent, it is bounded. When it is monotonically sequence and bounded, then it is convergent. Okay, a monotonic sequence is a fixed one. If it is convergent, it is bounded also. If it is bounded, then it is convergent also, right? So that's how we can just understand these 5 statements. And these 5 are of course important for us while discussing few other things in this particular chapter. Let's take few questions now. Look at this. Now let us take these questions one after the other. Now we need to test these sequences for convergence. Try to recall, when can we say a sequence is convergent? In simple, you see, you're writing them like this. See, in simple, you're writing them like this. When you are given a sequence Sn, if as n tends to infinity, if limit exists to this particular sequence, then we say the given sequence is convergent. The same thing we use here for the given sequence. I'll just calculate the limit. If the limit exists, we'll say it is convergent. If the limit doesn't exist, no, it is not convergent. That's what we can do. I'm just taking the first example here, you see. Now see, for this sequence, directly you are given the nth number. If the nth number is not given, of course we'll calculate the nth number also, but anyway nth number is given here already. I'm just trying to take what you call limit n tends to infinity Sn. So see what happens. Limit n tends to infinity. See, I'm writing it like this: 3n divided by, from the denominator, you see I'm just trying to take a n common. So when I take n common from the denominator, we'll get it as 1 plus 7n. So then it is equals to limit n tends to infinity. You can cancel this n, you see. So that we'll get it as 3 divided by 1 plus 7n. Now see, when you take n tends to infinity, it's clear 7n approaches to infinity. Right? When n approaches to infinity, 7n approaches to infinity, and therefore 1 plus 7n, all this denominator also approaches to infinity. When the denominator approaches to infinity, clearly, something, a finite value divided by some infinite value, will get this limit as, simply 0. So when n tends to infinity, the number 3 by 1 plus 7 approaches to 0. Therefore, clearly, the limit exists to this sequence. Therefore, limit n tends to infinity Sn is equals to 0. From this, you can say, therefore, the limit exists, and hence you can say the sequence is convergent. Since you are getting a finite limit here, the sequence is convergent. And you can also say Sn converges to what limit? Whatever the limit you got here, you can say Sn converges to that limit 0. So the first sequence is clearly convergent. Now let's look at the second one. Even for the second one, you need to take limit as n tends to infinity. But if you directly take n tends to infinity here, you see, you will get it as again infinity only. So we need to make some manipulation here. See, this is the actual nth term what you are given. Now I'm just taking rationalization here. Okay, let us see what happens when you take rationalization. So this is the one thing. I'm just multiplying and dividing this by root of n plus 1 plus root n. Right? Now see, if you just multiply these two, it's like a plus b into a minus b in the numerator. So it will be a square minus b square, right? So when you take a square, it is root of n plus 1 whole square, which is n plus 1, minus root n whole square, you see, it is plus n, divided by, you can write this as it is, n plus 1 plus root n. Now see, this can be written as, you can cancel this n here. When you cancel n, we'll get it as only 1 divided by root of n plus 1 plus root n. Now see, the same term, whatever you are given in the question, we can rewrite it like this. Now let us take, limit of this particular term. So therefore, limit n tends to infinity Sn is equals to limit n tends to infinity, all this, 1 divided by root of n plus 1 plus root n. Now see, if you take n tends to infinity to this particular, function here, what happens? You see, as n tends to infinity, clearly this denominator approaches to infinity only. That's how, you will get this as again 0 only. So as n tends to infinity, again this Sn approaches to 0. Therefore, you can say again the sequence is convergent. And also you can say Sn, the given sequence, converges to 0. Right? It is, just, accidentally we got both the limits as 0, but that may not be the case every time. Now let's look at this question. When you are given this sequence here, you see, I'm just trying to calculate limit n tends to infinity to this sequence. Right? See, while calculating the limit, if you directly, take n tends to infinity in this, we'll get it as simply infinity by infinity, right? So we need to make some manipulation. So I'm just taking it like this. If you look at these two terms, both the numerator as well as denominator, from them, I'm just trying to take the highest degree term common. So if you look at the numerator, the highest degree term there is n cube. So when I take n cube common from the numerator, we'll get it as 2 plus 7 divided by n square. Right, already here is an n. When you divide it by n cube, we'll get it as n square. And similarly, even from the denominator, if you take n cube common, we'll get it as 5 plus 3 n square by n cube, we'll get it as 3 by n. So this n cube can be cancelled here. Then it is equals to, we'll get it like this. You see, limit n tends to infinity. What it is? In the numerator, it is simply 2 plus 7 divided by n square. And in the denominator, it is 5 plus 3 by n. Clearly, you can see when n approaches to infinity, both 7 by n square as well as 3 by n, both approaches to 0. And therefore, we'll get this limit as only 2 by 5. As n tends to infinity, 2 remains as 2 only. But here, this 7 by n square approaches to 0. And in the denominator, 5 remains as it is, but this 3 by n approaches to 0. That's how you see, we'll get limit n tends to infinity Sn is equals to 2 by 5 here. Since again, you see, you are getting this as a finite value. Therefore, you see, again, here also, we say the sequence is convergent. By chance, if you get the limit as what you call infinity, or if you get limit as some other multiple values, then you say the sequence is divergent. And here the sequence converges to the number L by 2 by 5. Right? So like this, you see, you can check convergence of a sequence. Yeah, let's look at these two. Look at the first one here. Now it's Sn is equals to 2 plus minus 1 to the power of n. Right? See here what happens. If you just write all the numbers, you're actually given Sn is equals to 2 plus minus 1 to the power of n. In this sequence, if you take minus 1 to the power of n, it actually gives you two different values. For all even numbers, it gives you minus 1 power n as plus 1. And for all odd numbers, minus 1 power n gives you what you call minus 1. So certainly, they'll get two values. I'm just writing those two here. So therefore, Sn is equals to, when it is even, if n is even, we'll get minus 1 to the power of even number as plus 1. So that's how it is 2 plus 1, which is 3. So Sn becomes 3 if n is even. Right? Similarly, when n is odd, what happens to this? You see, minus 1 to the power of odd number, which is minus 1, So 2 minus 1, it is simply 1. So Sn approaches to 1 when n is odd. So therefore, you see, limit n tends to infinity Sn. Does it exist now? You see, when n tends to infinity, depending on when it is even or odd, we'll get two different numbers. So limit n tends to infinity is now 3 when n is even, and it is 1 when n is odd. In this case, you see, we can say, therefore, the limit doesn't exist. When it approaches to a unique finite value, then only we say the limit exists. Then only we say the sequence is convergent. But here, since you are approaching, since the sequence is approaching to two different values, we can say the limit doesn't exist and hence it is divergent. The limit doesn't exist and therefore the sequence Sn is divergent. Right? So this is one possibility. Now let's look at this question. You are given, all the sequence of numbers. Sn is equal to 1 by 3, minus 1, minus 2 by 3 square, then plus 3 by 3 cube, then minus 4 by 3, 4, 4, and so on. So this sequence has, alternating terms. One is plus and then it is minus. Then next again it is plus, then, minus. Alternately, you have positive and negative terms. I'm just writing all those terms here. What happens to this sequence here? Sn is equals to, look at these terms carefully. In every term, you have some 3 power, right? So I'm just writing that here. 3 to the power of n is there. In the first term, it is 3 power 1. Then it is 3 power 2. Then it is 3 power 3. Then it is 3 power 4. You see, You can just look at them. That's how, whether it is even or odd, whether it is first term or second term, definitely have this 3 power n. And look at this, you have, when it is 3 power 1, corresponding to that in the numerator you have 1. When it is 3 power 2, corresponding to that you have a 2 in the numerator. When it is 3 power 3, there is a 3. When it is 3 power 4, there is a 4. And in general, when it is 3 power n, we have n in the numerator. So the nth term looks like this, n divided by 3 to the power of n. That's one point. Then you see, when it is the first number, it is what you call a positive number. So when I substitute n is equal to 1, I'll get this as 1 by 3, fine, no problem. But when I take n is equal to 2, I must get it as negative, Not only for 2, even for 4 also we are getting negative numbers. In the sense, you can understand, for all odd numbers, we are getting them as positive terms. Right? For n is equal to 1, n is equal to 3, then for n is equal to 5, 7, like that for all odd numbers, we'll get positive terms. Then for all even numbers, you see, for 2, 4, 6, for all other things. For all even numbers, we'll get them as negative. That's how I'm taking Sn as n by 3 power n if n is odd. And I'm taking the same as with negative sign, minus n by 3 power n if n is even. Right? When it is even, we'll get the same term, but with negative sign. When it is odd, we write the regular term. So now these are the sequences. Now let me see what happens to these two when n approaches to infinity. And thereby I can decide whether the limit exists or not. And of course, I can also conclude whether it is convergent or not. Let me just take it like this. Limit n tends to infinity, Sn. Right? So let us say here n is even or else odd. Let me take, because we have written n as odd first. If I take n tends to infinity, but n is odd, then what happens to you? What happens to this? You see, in this case, limit n tends to infinity, when n is odd, Sn is actually this. So it is 3 divided by n to 3 to the power of n. N divided by 3 to the power of n. See here, you cannot actually directly take n tends to infinity in these two, because both numerator as well as denominator approaches to infinity. So what you can do, you can use what you call El Hospital rule. So that's how, when you use El Hospital rule here to calculate the limit, you'll get it like this: 1 divided by, I'm just differentiating both numerator and denominator individually. That's how, when you differentiate the numerator, it is 1. And if you differentiate the denominator, it is n into 3 to the power of n minus 1. That's how you see now, if you take n tends to infinity, we'll get only infinity in the denominator. And therefore, you see, when n approaches to infinity, this term, this Sn approaches to simply 0. So when n is odd, we are getting the limit as simply 0. Right? That's a good thing. Next, in a similar way, let us take limit of Sn when n is even. Now in this case, I'm taking n is even. When you take this, you see, in fact, a similar story with a negative sign, nothing else. Limit n tends to infinity, now it is minus n divided by 3 to the power of n. The same thing, right? I cannot take directly, n tends to infinity here. So I'm just trying to use, I'm just keeping this minus sign before this limit, and I'm using what you call El Hospital rule. So minus of limit n tends to infinity. Here also, if you differentiate that, we'll get it as minus 1 divided by n into 3 to the power of n minus 1. Again, the same story, you see, when n approaches to infinity, this term approaches to infinity in the denominator. Right? When it is infinity in the denominator, the limit is approaches to directly 0. In either ways, you see what happened, whether it is even or odd, you are getting the limit as directly 0. Therefore, you can say limit n tends to infinity Sn is 0. Right? You are getting a single unique finite value, 0. Therefore, you can say the given sequence Sn is convergent. Right? And of course, it converges to the number 0. Right? So like this, you can identify whether the given sequence is convergent or not.